Phosphorus is a key nutrient required for all living organisms. Without it, we would not be alive. Phosphorus is in our bones, is the backbone of our DNA, and in the form of ATP is the energy currency for living cells. Phosphorus is irreplaceable. This means that it can't be recreated in a lab or substituted by a different molecule. Our dietary needs for phosphorus are met by eating plants or animals that eat plants. Given this, phosphorus is a crucial component in agriculture and crop growth. Plants acquire phosphorus from soil. Since plants deplete phosphorus from soil over time, farmers must continually apply more phosphorus each year to ensure healthy crop growth. When farmers increase the amount of phosphorus available to these crops, there is increased crop survivorship, growth, and yield. The application of phosphorus is crucial for securing our food on the national and global levels. In fact, over 50% of our global population would not be alive today if we did not use phosphorus in agriculture. Knowing this, it makes sense that we would want to add lots of phosphorus to fields to help crops grow and produce more food. However, at the rate phosphorus is mined to meet up with the food demands of the growing global population, we are at risk of exhausting these resources. In fact, phosphorus shortages could occur within 30 years from now. Why? The answer lies in where phosphorus comes from and how we as humans manage and utilize this precious resource. 90% of the phosphorus that we use in agriculture comes from mineable phosphorus reserves. These reserves are in essence deposits of ancient organisms and are limited and non-renewable. However, at the rate phosphorus is mined to meet up with the food demands of the growing global population, we are at risk of exhausting these resources. For example, natural phosphorus reserves in the United States could be depleted in as early as 30 years from now. Even if we combined the total global supply of phosphorus, it would likely only last humanity up to 300 years. We also apply more phosphorus than the plant can absorb at one time. Crops typically absorb only 10 to 50% of synthetic applied fertilizers. The leftover 50 to 90% can remain in the soil in a form unavailable to plants, erode from the soil's surface, or wash off with rainwater and enter into the watersheds. This over-enrichment of phosphorus is toxic to aquatic environments. As many watersheds are low in phosphorus, this abundance of phosphorus provides excess nutrients for algal and other aquatic organisms and leads to algal blooms. Overall, the ways in which we utilize phosphorus are inefficient. This is the cycle of phosphorus use and efficiency. We mine our depleting supply of phosphorus in large quantities, apply large quantities to our farmland, and large amounts of phosphorus can enter aquatic environments and cause algal blooms. It is crucial now more than ever that we find new and inventive ways to recycle phosphorus and prevent a global food and fertilizer shortage. One innovative and exciting example to circularize the phosphorus economy comes from our lab group and our research using plants. The leaders of this research effort in our lab, Dr. Glenda Gillespie and Dr. Catherine Freed, are currently developing plants with a unique capacity to acquire phosphorus from nutrient-polluted environments. Once these plants absorb excess phosphorus, their biomass can be processed and reapplied to release phosphorus and other nutrients back into soils where phosphorus was low. By recycling what we already have available to us in the environment, rather than using mineable phosphorus, we can stop repeating the cycle of phosphorus use and efficiency and secure our global food supply.